Okay, so first we want to look at process layouts and try and come up with a way to quantify the value of a process layout or how expensive it is. And again, remember that our objective in process layouts is to minimize total movement costs. Now there's different ways to quantify total movement costs. What we're going to use in this example, and mostly what they use in the text, is quantifying movement cost as the footloads per time unit, here footloads per day. What I mean by footloads is if you have a load of parts, say a bin of parts or a pallet of parts, and you have to move that single bin 20 feet, that's 20 times 1 equals 20 footloads. And if you're doing that every day, that's 20 footloads per day for moving that bin 20 feet. On the other hand, if you had two bins that were being moved, each being moved 20 feet per day, that would be a total of 2 times 20 equals 40 footloads per day. Clearly, the more footloads you have, that means the more bins you're moving, the more distance, or the more pallets of parts you're moving, the more distance. That's a bad thing. That takes time. That costs money. So what you want to do is minimize the total amount of distance traveled by all these loads, or minimize the footloads. And that's what we're going to be using for total cost in this example. And again, that's the same thing they do in the text, although they don't really call it footloads. So there's two components to calculating the footloads per day that are being moved between a pair of work centers. Basically, we need to look at the distance between the work centers, and that's expressed in terms of feet. Okay, so distance between work centers I and J in a particular layout. And then we also have to say, okay, how many loads per day, what's the volume of flow that's being moved from work center I to work center J, and I'm going to represent that in my equation on there with the big V for volume, V sub ij. So if for a particular I and a particular J, that is a particular pair of work centers, we multiply the loads per day times the distance between those work centers, we get the footloads per day for the cost of those two work centers given where they're located in our layout. So that's just for one pair of work centers, and that's what we have here in the right hand side of this equation inside the summation. Okay, the footloads per day for a single pair of work centers. What the double summation does is then just say, okay, add that up. Okay, add those footloads per day up across all possible pairs of work centers, and that gives us the total cost in terms of footloads per day of our layout. Right? And we can compare then one layout with another layout, and we'd obviously want to go with the layout that had the lowest number of footloads per day associated with it. Well, let's take a look at a real small and simple example just to make sure we understand that and how it works. So what I have here, I have 3 work centers in this example, and the work centers are numbered very cleverly, number 1, 2, and 3. So what I have here is the volume matrix showing me what are the loads per day traveling that I expect to travel from work center 1, 2, or 3 to work center 1, 2, or 3. You'll notice that the matrix is a little sparse. I don't expect there to be movement from every work center to every other work center. It looks like all I expect to see is 300 loads per day moving from work center 1 to work center 3, and then 200 loads per day moving from work center 2 to work center 3. Okay, so fairly simple. The volume matrix just with 2 entries, that's going to make the equation a little easier. Just basically this double summation, which looks so nasty, will just have 2 elements in it when it's expanded. Up here I have the distance matrix. You'll notice that this is expressed in terms of locations in the new facility. The locations or rooms are labeled A, B, and C. This is a schematic floor plan representation of my new facility, and I have the distance from each room to every other room. So for example, between A and B, that's 40 feet. From A to C, okay, that's 60 feet farthest apart, and then the closest 2 rooms or closest 2 locations are B and C, they're only 20 feet apart. So this very simple problem, I could probably just eyeball it and figure out the best assignment of work centers to locations, but let's pretend that I'm really dumb and I'm not going to do that, and I just want to arbitrarily assign work center 1 to room A, work center 2 to room B, and work center 3 to room C. And then I want to just cost that out, see what the total cost is in terms of footloads per day. Well, here's my distance matrix from the previous page. Here's my volume matrix. There's the formula I had. And again, as I said earlier, since I only have volume flowing from work center 1 to work center 3 and work center 2 to work center 3, I'm only going to have 2 elements in my total cost equation when I expand it out. I don't need to write out the ones that are going to end up being 0. So I write out the equation here for the pair of departments from 1 to 3 and from 2 to 3, and I see that the volume going from 1 to 3, that's 300, and the volume going from 2 to 3, that's 200. And then I just got to fill in, based upon this assignment of work centers to rooms, what the distance is from 1 to 3 and the distance from 2 to 3. And again, since 1 is in A and 3 is in C, the distance from A to C is 60 feet. That's the distance in between 1 and 3, so right, 60 feet. And since, to find the distance between 2 and 3, since 2 is in B and 3 is in C, that distance between B and C is 20 feet. And again, that's what I write down here. So costing this out, I get 300 times 60 plus 200 times 20. That equals 22 grand or $22,000. That's the probably really shouldn't have this dollar sign here. Those are, sorry about that, those are footloads, not dollars. So that's 22,000 footloads per day is the total cost of that that layout.